Alright guys, in this video we are going to put together sections 5.2 and 5.3. They're both about rational functions. Rational functions you can also think of as fraction when you hear rational. They're in the form of p of x over q of x, where p and q are polynomials. So we have a function that's in the form of a fraction, where we have a polynomial over a polynomial. So the first thing that we're going to do is we're going to review domain a little bit. We've already looked at this. Let's start with r of x equals x plus 2 over x plus 3. Okay, so this is a rational function. We've seen something like this before. It's a polynomial over a polynomial, so these are not unfamiliar. And remember, when we're looking at domain, we're looking at the allowed x values. So for a fraction, the only thing that we have to worry about is a 0 in the denominator. So for the domain, we need to know where is x plus 3 equal to 0. And that's what we cannot have in the domain. So we know for this one, probably just by looking at it, that when x equals -3, we've got a 0 in the denominator, and that's not allowed. So our domain is going to be that x cannot be equal to -3. Or if you remember in set notation, x such that x is not equal to -3. Okay, so we did that before. That part should look familiar to you. Now we can look at things that are maybe a little bit more complicated. Let's say we have the fraction x over x squared minus 4. X over x squared minus 4. Well, we want to know where the denominator is equal to 0. And in order to see zeros, remember from our last section in 5.1, it's easier if it's factored. So let's go ahead and factor this. The top stays the same. The bottom is the difference of two squares. So that's going to factor as x plus 2, x minus 2. Okay, so this is the same function right here, just in factored form. And now we say, okay, where is x plus 2 times x minus 2 equal to 0? And we know from the polynomial section we can see the zeros right here. From this factor we get -2, and from this factor we get +2. So our zeros are at -2 and +2, so that means our domain can be anything except plus or minus 2. So our domain is x except for plus or minus 2. So we can put together now what we know about polynomials with what we already knew about domain. Okay, so let's look at this idea of zeros in the denominator a little bit more. We've looked at it with domain, but what does it mean? What happens when we have zeros in the denominator? I'm going to leave a little bit of space right here to write some more, but let's look at an example. So let's say that we have, hold on, my tablet's freezing a little bit. Okay, let's say that we have r of x is equal to x plus 2 over x squared minus 4. We looked at one that was similar to this just a minute ago. Okay, so we know that to find zeros in the denominator, we want to have this factored, and it turns out we want to factor it completely. So the top is already factored, and we know that the bottom factors as x minus 2, x plus 2. Okay, so what's going on here? Well, what happens when we get close to +2, okay, when x is close to +2, if you remember from when we looked at the graph of 1 over x, remember as we got closer and closer to 0, this thing started getting bigger and bigger, and it gave us that L shape with an asymptote. So what happens when we get closer to +2, these numbers, let me put it in red, these numbers right here will match, and so basically they'll cancel out. And what happens when we get close to +2 is we start getting 1 over 0. We get closer and closer to 1 over 0, which goes towards infinity. And what that means is when we get close to +2, we're going to have an asymptote. Just like we saw at x equals 0 with 1 over x, if you remember talking about that graph. So when we get to close to +2, we get an asymptote. All right, well, what's going on over here with this +2? What happens as we get close to -2? Okay, we get a 0 here at -2. That means the graph does not exist. But what happens everywhere except for -2, these are going to cancel out. So it cancels out everywhere except -2. Okay, every other number is going to cancel out. Okay, cancel, cancel. Except at -2, it does not exist. So what happens here is the function's going along, everything's fine, but then at -2, we end up with a hole. Okay, so because these cancel out everywhere except for right here, we get a hole. But this one has nothing to cancel out with, we get an asymptote. Okay, so to look at these in general, zeros in the denominator become a whole if the factor matches the numerator. Let me get this out of here. Okay, a whole if the factor matches the numerator. And it becomes an asymptote if it does not match. Okay, so if it does have a match, it becomes a whole. If it does not have a match, it becomes an asymptote, and it has to match exactly. Okay, so what this graph ends up looking like, and I don't expect you to be able to draw these yet. Okay, what this graph ends up looking like is something like this. We've got, at +2, we've got an asymptote. We know that looks like a dashed line. And at -1, we're going to have, -2, we're going to have a hole, but we would have to know what the graph looks like. We don't know that yet, but it ends up looking something like this. And we get a hole at -2, and it goes along like that. And we've got that piece like that. Oh, I got a little bit too close to the asymptote, didn't I? Remember, it should not actually touch the asymptote. Okay, so what you see here, you see at +2, we've got the asymptote right there. And at -2, we've got a hole. And then how we get the rest of this picture, we're gonna talk more about that. Okay, right now we're just looking at the asymptotes and the holes. Okay, let's try this one. Let's see if we can find vertical asymptotes and or holes. They might not have either one, they might not have both, but let's check and see. So the first thing that we want to do is we want to factor, because we have to see if the factors match. So factor the top completely, factor the bottom completely. So the top factors is x plus 1, x minus 1. It's the difference of two squares. And on the bottom, we're looking for factors of 3 that add up to 2. So x plus 3, x minus 1 should do the trick. They multiply to be -3, and they add to be +2. Okay, so now what do we have? Do we have any vertical asymptotes? Do we have any holes? So remember, for vertical asymptotes, we're looking for zeros in the denominator. Okay, so what are our zeros in the denominator? We've got -3, and we've got +1. So that's either going to become a vertical asymptote or a hole, and same thing here. So for -3, do we have a factor that matches on top? No, we do not. There's not a factor that matches, so -3 is a vertical asymptote. Okay, now moving on to this one. +1 came from this factor. Do we have a factor on top that matches? Yes, we do. So that means that this becomes a hole. X equals +1. This other factor over here, it ends up being the x-intercept, but we're not going to worry about that part. So any zeros on top, you don't have to worry about. You're just looking to see if they're going to match or not. All right, so this picture ends up looking a little bit like this. Let's see, we've got 1, 2, 3, 4, 1, 2, 3, 4. We've got an asymptote at -3. Okay, we see that vertical asymptote at -3. And then the graph ends up looking bit like this. We've got an L-shaped piece right there, and we've got an L-shaped piece right there, and I've got to go back and add in the hole right here. Okay, so we've got a vertical asymptote right there, and we've got a hole right there.